Hello, my name is Alejandro Martinez and this is my chemistry on. I'm going to be talking about the chemical reaction where magnesium carbonate yields magnesium oxide and carbon dioxide. This is a decomposition reaction because you have one reactant and two products. So the overview of this video, I'm going to be talking about some of the information of the elements in the chemical reaction. I'm going to balance the chemical equation. I'm going to calculate the enthalpy of reaction, and then I'm going to see the energy released, and then I'm going to calculate the temperature change of the water. Some facts about magnesium. The element symbol is Mg, stands for magnesium. It has an atomic number of 12, meaning it has 12 protons in a single magnesium atom. It also means that in a neutral magnesium atom there are 12 electrons. Has an average atomic mass of 24.31. It's in group number 2, period number 3, and it's an alkaline earth metal. Its electron configuration is 3s. And I'll be talking about carbon. Carbon's element symbol is C, has an atomic number of 6, meaning there are 6 protons in a carbon atom, and in a neutral carbon atom there are 6 electrons. Has an average atomic mass of 12.01. Group number 14, period number 2, and it's a non-metallic atom. Its electron configuration is 2p. Oxygen's element symbol is O. Its atomic number is 8, meaning there are 8 protons in an oxygen atom, and in a neutral oxygen atom there are 8 electrons. The average atomic mass is 15.999. Its group number is 16, it's in period 2, and its family name is a chalcogen. Its electron configuration is 2p. So here we have the chemical reaction, and I'm going to balance it. So the first thing we want to do is we want to, separate the equation along the yields or the arrow. So on the left we have the reactants, and on the right we have the products. So now we want to create a list. So magnesium, there's only one molecule of magnesium. Carbon, there's only one, and for oxygen there's 3 because of the subscript. On the product side we have again one molecule of magnesium, we have one molecule of carbon, and for oxygen we have 2 molecules plus the magnesium oxide, which has 1 molecule of oxygen, therefore being 3. And you can see that this chemical equation is already balanced. So we did not have to alter anything by adding coefficients. It was simply balanced. So to calculate the enthalpy of a reaction, you have to use tables of enthalpies. And here I have the enthalpy values of the reactants and products. So what we want to do is get the products and subtract that from the reactants. So we add the enthalpy values of the products together, which is magnesium oxide and carbon dioxide, which is negative 995.3. And then we want to subtract that from the reactant, which is negative 1113, which ends up being a positive value, and you're left with 107.7 kilojoules per mole, and that is the enthalpy of a reaction. In order to calculate the energy release, if there are 250 moles of product, all you have to do is take your enthalpy and multiply that by 250, which is 29,425 kilojoules per mole. Now 1 kilojoule is 1,000 joules, so we multiply 29,425 by 1,000, which gives us the amount of energy released. The temperature change of the water, we want to know what we have. So we know there's 1,000 grams of water. It's at 21 degrees Celsius, and the energy required was 29,425,000. First thing we want to do is we want to find out how much energy is required to take the liquid up to the gas state. And in order to calculate this, we use the equation Q equals m times C of I times delta T. Q is the total energy, m is the mass, Ci is the specific heat capacity of water in the liquid state, and delta T is the change in temperature. Now, specific heat capacity is how much energy is required to change the temperature of one single molecule. So we know there's 1,000 grams. So the specific heat capacity of water is 4.8 joules over grams degrees Celsius times 79 degrees Celsius. We get to 79 because the boiling point of water is 100 degrees and we start at 21, so 21 plus 79 equals 100. That equals 330,220 joules. Step is to determine how much energy is required to take that, 1,000 gram water from the liquid state up to the gas state. And to do this, we use the latent heat of vaporization, which is Q equals M times H of delta vaporization. M again stands for mass, and H of delta vapor is the latent heat of vaporization, which is how much energy is required to take that anything from the liquid state to the gas state, or anything from the gas state to the liquid state. And for water, it is 2,260. So we multiply that together, grams cancel out, and it's 2,260,000. The next step we want to do is we want to find out the total energy it took to bring the water from the liquid to the gas state, which was 2,590,220. Now we want to subtract that from the total energy, which is 26,834,780 joules. Now the next step is to use the energy just found as our Q, and for specific heat capacity we're going to use 1.99 because that's the specific heat capacity of water in the gas state. We want to see how far the temperature reaches in the gas state, so we use 1.99, and we leave delta T because that's our variable we want to solve. So now we just solve, we plug and chug, we reduce, and our final temperature is 13,484,081 degrees Celsius. And we want to add that to 71 degrees Celsius because we want to find out the total energy it took to reach the gas state. And our total is what you see in blue. Thank you for taking the time to listen to this video. I hope you learned a lot from this video, and you can check out my other videos in my YouTube channel. Thank you.